Welcome to Higher Structure Seminar Series of State Center for Physics and Mathematics. Today our speaker is John Huerta from Instituto Superior Técnico Lisbon, and he will talk on Poincaré duality for families of supermanifolds. So we thank John for giving this talk. Yeah, please, John.
All right. Well, I'd certainly like to thank you for inviting me to give this talk. And let me preface by saying that, first of all, I have a cold, a bit of a cold, so I may be a little hoarse. And second of all, this is the first time I'm giving this particular talk, so there may be a few kinks that I haven't worked out yet, and I apologize for that. But let's see. So I want to tell you about Poincaré. Oh, and one more thing is that feel free to interrupt me with questions if you have any questions. I'll do my best to answer them. Okay, so I want to tell you about Poincaré duality for families of supermanifolds. And first, I should tell you that this is joint work with Constantine Eder and Simone Noha. And you can find our paper on this, including a bit more stuff, because we also think about some applications to supergravity that I won't be talking about today, um, in this archive preprint number. So let's get started. So first of all, let's recall how classical Poincaré duality works. And by Poincaré duality here, and almost Poincaré duality here, I mean for um, de Rham cohomology, not for integral cohomology, although certainly there is a version. Um, so I'm going to consider a manifold M, which is oriented. It's n-dimensional. It's smooth, and the boundary, it has no boundary. So, if you recall, if you were introduced to this subject by, say, reading or studying the textbook by Bott and Tu, Poincaré duality for de Rham cohomology is induced by a pairing. And it's a pairing that pairs P forms on M with complexly supported N minus P forms and produces a number. And it's given by wedging and integration. So if I have a P form and a compactly supported N minus P form, then I'm just going to map that to the integral over M of alpha wedge beta. And this induces an iso, a linear iso, on the cohomology groups given by de Rham cohomology in degree P. And
I'm sorry, I
compactly
guess there is a
supported.
problem in the. Oh, okay.
Is everything okay?
Yeah, now we
Okay.
can see. Yeah.
Compactly supported de Rham cohomology in degree n minus p. So that's the story that I'm trying to generalize to supergeometry. And it's going to generalize in two different directions, which is that. So, yeah. So yeah, I want to generalize the above to M a supermanifold. I will tell you what that is, at least very briefly. can you hear me?
Yes, we can hear you now.
Okay, sorry about that. I was connected to Ethernet, and maybe the Wi-Fi is actually better here than the Ethernet.
I see.
I've now
Yeah.
turned on my Wi-Fi.
Yeah.
Let's see if it works. So when I disappeared, did my tablet also disappear, or was it still
No,
visible?
I mean, but it is now stable. Uh,
Okay, okay, good. All right, let's see how this goes. Anyway, I was saying that I want to generalize the above result on Poincaré duality for classical manifolds and de Rham cohomology to supermanifolds. And there are two directions that I will need to generalize it. First of all, the integral of alpha wedge beta does not make sense for M a supermanifold. And so this is an end form, aka a top form. And in supergeometry, we don't actually have top forms. The de Rham complex, the complex of differential forms, will be unbounded above. So we're going to need to integrate something else. And I will get into what that is in a minute. And another direction to generalize it, which is much less obvious, even if you know some supergeometry, is that we should consider, instead of a single supermanifold, we should consider families of supermanifolds. So here, this is the base supermanifold. It parameterizes this family, and the top here is an S parameterized family of supermanifolds.
can you say a few words what a supermanifold is, John?
Yes, I will get into that next. So, but first, let me just say that this is what I want to, this is the story I want to tell. I want to tell this story where I generalize the theory of integration, and I also generalize the theory to families. Um, and so let me just briefly say how the talk will go. So, so the next part is going to be an answer to your question, which is that I'm going to introduce supergeometry and integration. Um, then I'll tell you about differential forms, aka the de Rham complex in supergeometry. And I mean, I can tell you right now, it's almost exactly the same as the classical story. But in supergeometry, we have something new. And that something new is that we have a new complex, and the forms in that complex, in contrast to being differential, they're called integral. And these new forms, these will be the forms they're called integral because it's appropriate to integrate them on M and on sub manifolds of M. So that's going to be part of our answer. And then I will tell you about families. And I'll briefly introduce the relative point of view to how to generalize everything that we've said so far to the situation of families. And I'll state the main theorem, which is going to be Poincaré duality in families. All right. Any other questions besides um, describing what a supermanifold actually is? Okay. So let's get into the main body of the talk. Supergeometry. and integration. So just like before describing what a manifold is, you have to do a little analysis. To do supergeometry, you have to do a little what's called superanalysis. So there was this mathematical physicist in Russia named Felix Berezin, and he was studying quantization. He was interested in the quantization of fermions, and that led him to this idea, which is that one should do analysis with anti-commuting aka oh my god, aka Grossman variables. And mathematically, what a mathematician might say is that we're going to work in the exterior algebra. So um, so let me take an exterior algebra, and I'm going to name its generators. I'm going to name p different. Well, do I want to p or n? I think I'll do n. And part of Berezin's idea was that you should think of this as the algebra of functions on some space, some mildly non-commutative space. And that space um, is going to be denoted by R0 slash N. This is going to be the algebra of functions on this space. And theta 1 through theta n are the coordinates, the coordinate functions for this space. So, like I said, Berezin wanted to do analysis. Um, and differentiation is not so hard. The way that you differentiate with respect to the variable theta I is you just delete it from one of these wedge products, if it occurs. So if I have a wedge product and there's a theta I in it, then the derivative is just that same wedge product with the theta I gone, and a sign. The idea being that the derivative operator is odd. It has an odd degree. So if I move it through the theta i's to get the one that it can get, then I'll get signs as I do that. Or alternatively, I could move the theta I. I could move this theta I to the front, and then I'll get signs. And then if I take the derivative, I just get one, but I still have a sign. Are there any questions on that?
So, I mean, here Berezin more or less uses the idea of Grothendieck that, I mean, in order to study a geometric object, it suffices to know the functions defined on this object. So he
Yes,
considers these functions as the Grassmann algebra. Uh,
that's right.
okay,
That's exactly right. Yes.
okay, so I understand. Thank
And in those functions, he's trying to define a kind of calculus. He's trying to define analysis.
you.
And let me explain this. Let me explain the differentiation option a little more clearly. If I have theta I and I just differentiate theta j, then I get delta ij. So I get one if it's the same and zero if it's different. And to differentiate a more complicated expression like the expression above, I just need to move this to the front and then apply the derivative operator. So I get a sign. That means that unlike unlike classical derivatives, theta I, the derivative of theta I and theta j, they anti-commute with each other. But beyond that, there's not much difference, at least in terms of the algebraic properties. Okay. So now, what about integration? So integration is more interesting. So we want to define a linear operator, which we're going to call the integral over 0 r0n. And I'll put some kind of measure in here, but this is not going to be the usual measure. That's why I've put some brackets around it to distinguish it. And it's going to be an operation that takes elements of this exterior algebra and produces a number. So we need to define this. So Berezin is trying to define these operations, and the one guiding principle is that if you integrate a derivative, then by integration by parts, you should get zero. So exact terms should have vanishing integral. So maybe I'll go ahead and ask the audience what expressions are not derivatives. So I have a basis for this algebra. It's a linear basis. It consists of all the wedge products, the p-fold wedge products from p from 0 up until n. And to define this linear operator, I just need to say what it does to this basis. So does anyone see which basis elements are not exact? They will not be, they are not derivatives of something else.
So, I mean, we have to look at wedges where theta i's are different, or all of them are different, or kind of thing.
Yeah, they've all got to be different. Because if any two of them are the same, then wedging them together is going to
Would
give
be zero.
zero.
Right.
and then the rule is that whatever they are, if they are a derivative of something else, then the integral is going to be zero. So I'll go ahead and give the answer, which is that the only possibly non-zero term is where you have the wedge of everything. So this is the only term that could possibly not be non-zero, because if you have the wedge of less than all of the thetas, then you could pick another theta that's not in the product and wedge that with it, and then take the derivative with that new theta, and you're just killing it off again. So it's a derivative. It's got to be zero by the first rule. Does that make sense?
Well, yeah, it makes sense when you answered the question.
Yeah, I'm sorry for taking that away, but and so usually this product with this order of thetas, it's the only one that could be non-zero. So we choose an order to be our favorite order, and we just declare that that has integral one. So that's the beginning of the story of Berezin integration. Um, and so, excuse me. So you could ask, what is this funny expression that I've written dn theta with brackets? So the first thing to note is that dn theta is not an end form. For n equals 1, if you have an end form and multiply theta by some constant number, that's just going to come out. Like I said, forms in differential forms in supergeometry are going to work basically the same as they do in classical geometry. So this is what it would do if it was a form. But but if you have it for but if you have this funny thing where I've got these brackets around the thing that I want to integrate against, then it's going to turn out that the lambda comes out as the inverse, as the reciprocal. So of course this only makes sense if lambda is non-zero. And the reason for that is we've defined theta integrated against this measure to be 1. So if I want to be invariant under the change of variables, where I just multiply by a number, sorry, I just multiply by some non-zero number, then that's going to imply this transformation property. Because I'm going to need, if I want these to be equal, that's the thing that I'm postulating. I'm sorry, I am a mathematician, but I'm not making my hypotheses very clear. So I've got a change of variables where I multiply theta by a number, but I want the integral to remain unchanged. And for that to be true, then this number needs to it needs to come out as the reciprocal in order to cancel the lambda in front of the theta.
I guess there
Is
is a
that clear?
question.
Yeah.
Uh,
Yes, I would like to ask a question. Then, what is uh, the theta in brackets?
What is the d? It's just notation. It's just at this point, it's just notation. It's some kind of it's supposed to be some kind of measure, but it's not a form. It doesn't behave the way that our measures, the way that we're used to the top form behaving.
Because yes, there's also a bracket in brackets d in parentheses lambda theta, and theta comes out as a reciprocal,
That's
and
right.
and in brackets the delta theta d theta. I don't know it.
Yes. So it's just notation for
Okay.
whatever the appropriate object is to integrate on a supermanifold. And I'm going to tell you in a few minutes now what it really is.
Okay. Thank you very much.
But I'm kind of developing the theory by examples because, well, I think this was actually how it was developed originally, was by computing these examples. And the two assumptions that I have made here, the assumption that I have made, let me illustrate the assumptions. So, so I've assumed this property. First of all, I've defined differentiation, and I've assumed this property that if I integrate a derivative, it has to be zero. And by as a consequence, that implies that the only interesting derivative you can have is where you wedge all of the coordinates together. And so that's the only possible non-zero term in this integral. And by convention, I've decided to normalize that term, whereas to make the integral just be equal to 1. And now the question I'm trying to answer
Can I
is,
ask something?
yes, please, absolutely.
R, when you write R0n, what should we think about as the space over which we're integrating? What is the 0 bar n stand for?
Yeah, that's a great question. And the answer is that I'm thinking, like Ilhan said a minute ago, I'm thinking of a space. This is a fictional space. I'm thinking of some kind of space where the algebra functions on that space are the Grossman algebra or the exterior algebra with n generators. And that is the definition of what R0n is. It is the space whose algebras of functions is the exterior algebra generated by these thetas. Does that answer your question?
Mm, uh, yes. Is there a reason why we have a 0 bar n in
Yes,
the
because there's also supposed to be um Rm.
kn?
So
Oh,
yes. So these are good questions. Um let me answer them now. I will go ahead and answer them now. So the reason is that we're supposed to have an Rm/n. We're, we are going to consider supermanifolds of this form with m ordinary even dimensions and n odd dimensions. And this is the space This is the space defined to be the space where the algebra of functions on it, like I said, it's all defined in terms of these algebras of functions. This is all like inspired by Grothendieck's approach to algebraic geometry at bottom. The algebra of functions on this space is just the usual C infinity algebra of functions on Rm. Tensor the exterior algebra on n generators. So with this definition, R0/n is the space I've been considering so far. And Rm/0 is just our usual Rm as a manifold, as some smooth manifold. In the Grothendieck point of view, you could think of it as that space whose algebra of the functions are all the smooth functions on the manifold. Does that answer your question?
Yeah, for the moment, yeah. Thank you.
Okay, good. And it was a useful digression because in fact, in contemplating this analysis with anti-commuting variables, anti-commuting coordinates, Berezin defined the integral over this more complicated space, Rm/n. And again, I'm going to use this notation for the thing that we integrate, the measure. And again, it's supposed to be a linear function that takes elements of the algebra of functions and spits out a number. So what do these functions look like? So an element in here depends on x and theta. And it's just an expansion of, it's the power series, so to speak, where I have smooth functions as coefficients. And then these thetas, these wedges of thetas, this is going too far off the screen. In fact, it's usually in supergeometry, it's normal to not write the wedge between the thetas. They're understood to always anti-commute with each other. Um, so at some point, I may start doing that by accident. So these are the elements that I want to integrate in this new unusual space, Rm/n. And the way the integration is defined is, again, the only interesting term is the one with all of the thetas. So it is defined by f of x theta, this weird notation that I'm introducing. To be the integral of the term with all of the thetas, and that all of those thetas integrate to 1. This is the definition. And then you just integrate the rest of it in the ordinary way. So now the brackets are gone. That is an end form. Or sorry, an M form, because this is M even dimensions. So that's the ordinary integral. So the thing I'm doing here now, the intuition, is that I'm kind of doing Fubini's theorem. Like I'm kind of writing this Rm slash n as Rm 0, which remember is just Rm, times R0 slash n. And I'm integrating out one factor, which is the R0 slash n, using the previous definition I gave, which is that the integral of all of the thetas is just 1. Any questions on this?
So this is a linear functional, this becomes, right?
Yes, this is a linear functional. This is just an R linear functional on this space of functions.
The lower indices for F are they derivatives or are they just coordinates of F?
So F is a function depending on two variables, or well, they're not quite variables. It's depending on two kinds of coordinates. It depends on the coordinates x, which are the commuting coordinates on Rm, and the coordinates theta, which are the anti-commuting coordinates on R0 slash n. And so the way that it is defined, this space of functions is just defined to be this tensor product. And that means that elements of this space of functions look like sums
Oh, okay. They are the
of smooth function
coordinates.
times the wedge products.
Right.
And that's all that is. You could think of it, and the way that people do think of it is that it's like expanding fx theta in a power series in theta. But you don't have to, because we have the definition. That is what it's defined to be. Okay, so that was a useful digression, because instead of knowing what this bracketed thing is with just thetas, I actually want to know what it is when it has x's as well, because I'm not just interested in doing the case where I have only thetas. So that's my question now, is what kind of an object is this? And I realize I may not really get to my main theorem, but that's okay. Um, so like I said, what we observed previously is that when m is 0 and n is 1, then the change of coordinates formula, if we demand that the change of coordinates formula hold, it implies that just the linear change of coordinates of rescaling by lambda, I have to get a 1 over lambda in front of this weird bracketed thing. But when m is 1 and n is 0, what is the corresponding result? Now it's just a commuting coordinate. But just to try to make sure that people are still with me, what's going to happen?
So
So
lambda
remember that, yeah, can you
lambda
hear me?
depends on x, or lambda is just a constant. Uh,
Lambda is just a constant
so
in
we
both of
just take
these.
lambda out.
Yes, that's right. So the thing is that when there's no odd stuff, when n is 0, it is just actually a form again, because that's how the integral is defined. You integrate in the ordinary way over the commuting coordinates, and you integrate in this funny way where you pick the top term over the anti-commuting coordinates. So it's just lambda times dx. All right. So now one more example for general N and general M and A and B matrices. Then the change of coordinates, the linear change of coordinates where I change coordinates by A for the x coordinates, and I change coordinates by B for the theta coordinates. The thing that this calculation is going to show, if you work it out, is that I get the determinant of A divided by the determinant of B times this funny thing that we're trying to figure out what it is. And that's shown by diagonalizing A and B, and then you have to show that, yeah, you have to show that you can do this in a way where you just get the products of the eigenvalues.
It is like the Jacobian kind of thing, right? This
It's kind of like the Jacobian. So this is actually an analog of the Jacobian. This is the super analog of the Jacobian. Okay, so let's try to get a little deeper into what this is. And the key observation is the one you just made, which is that it's like the Jacobian. Um, so so we need to take the Jacobian, but replace the ordinary determinant with a super version. And there is a super version, and it's called the Berezinian. So this now is a linear transformation for, yeah, what do I want to do here? Oh my God. I feel like this is so poorly motivated and introduced. So linear transformation of A modules for A some supercommutative algebra. And I take the free module with n even basis elements and n odd basis elements. And then I get this kind of matrix, this block matrix, because A just goes from A, oh my God. This is an algebra. A is a matrix. A just goes from the n by n part, the m part to the m part. It takes the even part to the even part. D goes from the odd part to the odd part. And the other elements can mix them. And there is a crazy analog of the determinants, which, like I said, is called the Berezinian, and it's given by a rather horrible formula. Maybe should I give the formula? I am a little unsure. What was it? I need to remember what it was. That's how bad it is. So this is so if you see that if you take this in the case that we were considering, where I just have A and B, A acting on X's and B acting on thetas, then you see that in this case, where this is a diagonal block matrix, I get exactly the kind of formula that I was seeing earlier from my Jacobian analog. And even though the formula is bad, one can prove, and Berezin did prove, that this is a multiplicative map on matrices over a supercommutative algebra, a bold, the supercommutative algebra. So we have the property, the standard property with the determinant, that if you have two of these matrices, now called X and Y, and you take their matrix product, you get the Berezinian of X times the Berezinian of Y. And it also has a very nice relationship to the trace, which is that if I have the exponential of some supermatrix, then the Berezinian of the exponential of the supermatrix is the exponential of the supertrace of that matrix, where the supertrace of A, B, C, D is just defined to be the trace of A minus the trace of D.
Can I ask a question? So
Of
on
course.
super manifolds, do we have a theory like super D algebra kind of thing?
Yes, definitely. Yeah, there's a theory of super Lie algebras, which has a very interesting representation theory. But every super Lie algebra is the Lie algebra of some supergroup, of some group in supermanifolds.
Also, the Lie theory extends.
Every finite dimensional one, sorry.
I
But
see.
yes, there is a Lie theory in the super world, and it's really interesting. it's some of the most interesting parts of the superworld
But how
because
about cut smoothie type of thing? I mean, affine D algebra for infinite dimensional setting. Do we have?
yes, those also exist and they're quite important in areas like superconformal field theory. So yes, we also have those. But as in the finite dimension, as in the classical infinite dimensional case, they are not all the Lie algebra of some group.
Thank you.
All right, so like I said, I want to understand with this strange thing that I'm integrating over. Um, so to just remember,
Another
yes, please.
question. What's the reason for the first coordinate being even and the second coordinate being odd in number? Well, maybe coordinate is not the right word, but
Yeah,
when we had
which one?
when we had RMN, the Grassmannian algebra coordinates, that has to be odd, and the regular coordinates number has to be even.
No, no, they need to be they. So I may have said
The,
that. I may have. So these numbers can be any number. M and N
okay,
can be any number.
okay,
I was using odd and even in the sense that the x's, the mx coordinates are even in the sense that they're commuting coordinates,
okay, yeah,
and the thetas are anti-commuting
anti-commuting
coordinates,
thing.
and
Okay,
therefore odd in two senses.
okay, thank you.
Sure. So remember that my goal all along here has been to understand this strange thing that I'm integrating. And to do so, what is it? So we want to understand what kind of an object this is. So we should work in a coordinate-free setting to make this easier. So let me introduce supermanifolds. So this definition is due to Dmitry Laitis, who was a student of Berezin. A supermanifold of dimension m/n, everything in the superworld has a pair of dimensions, an even dimension and an odd dimension, although the numbers can be any number. Um, is a locally ringed space M So this is very much in the tradition of Grothendieck. Like this is how the definition of a scheme goes. But it's a little simpler just because we're working in the setting of smooth geometry. So we have lots of functions available. So where MB is a M dimensional smooth manifold. And O on M is a sheaf of super commutative algebras. And here's the key thing is that locally, this needs to be isomorphic to R M slash N. So I can always find for every point in M little lower b, I wrote B for body, by the way. This is sometimes called the body. For every point in the body, M lower b, I can always find a neighborhood where that neighborhood can be identified with a neighborhood of Rm, of course, because it's a smooth manifold. But then the sheaf of functions on it, O of that neighborhood, can be identified with the smooth functions in Rm, tensor the exterior algebra on N generators. So that's the definition. Um, and let me just say that the de Rham complex works as classically, except it's unbounded above. So I can get up to dimension M. That's where we'd usually stop classically. But then it just keeps going. There's an omega m plus 1 and omega m plus 2, etc. And the reason for that is because the thetas anti-commute, the d thetas actually commute with each other. And that means that if you square a d theta, you do not get 0. So it never stops for this reason. Any questions on that? I'm almost out of time here and have barely, yeah, I definitely am not getting to my main theorem. But let's just consider this an introduction to supergeometry instead.
Excellent. I mean, we really learned what a supermanifold is. Yeah.
So let me now get to the question that I've been asking throughout the talk. Never mind the Poincaré duality that I meant to get to, although maybe I can get to a version of it, which is not the version in our paper. It's not for families. But let me just briefly get into this question that I keep repeating, which is what is this strange object that I'm using as the measure for a supermanifold, for integrating on a supermanifold? So I have this Berezinian map, and it acts as a superdeterminant. But look at the formula for it, and note that it's not defined unless D is invertible. So, and in fact, I haven't described it well enough to see it, but A needs to be invertible as well. And it turns out that this whole linear map needs to be invertible in order to define it. That's this big contrast with the ordinary determinant, where you can use the determinant as a test to see if you are invertible. You don't, there are no matrices where you take their Berezinian and you get 0. So that means that the Berezinian is actually a map from GL M slash N. So these are all the invertible matrices of this size with coefficients in A to GL 1 slash 0 with coefficients in A. It's a homomorphism. That's what this property that it's multiplicative says. And so that means when you have a representation of GLMN, then we can take in differential geometry, that means we can take associated bundles. So if you take this representation, the Berezinian representation, so that means that I can define the Berezinian of M to be the associated bundle to the frame bundle of my supermanifold over the Berezinian representation of GL1 slash 0A. And in fact, what actually ends up happening is that this strange object, dnx, dmx, dn theta, is actually a section of Berezinian of M. So that's finally what it is. It is a section of a bundle that we get in super geometry. And those are the things that you want to integrate over supermanifolds. And because GL1 slash 0 is one dimensional, you can think of this, you can extend this bundle, in fact, to a line bundle. You can add a 0 section. So it's a section of a particular line bundle. And I'm going to call the line bundle version of this associated bundle. Actually, I shouldn't even do this. Hold on, let me fix this slightly. So I don't want to actually take the associated bundle where I replace the fiber with this GL01. I just want to take the associated bundle where I replace the fiber with R1 slash 0. And I'm using the Berezinian here to get my representation. So this is like the bundle of all volume forms on M. And there are two ways to get the de Rham complex in classical geometry. So classically, a second way to define the de Rham complex, omega bullet of M, where M is now a classical manifold, is there are two ways. You could start in degree 0 and build up by taking the exterior derivative. Or you could start in the top degree and go down by taking the interior product with a vector field. So I can identify omega m minus m via the interior product. I can identify that with the space of all vector fields tensor the top degree. And I can keep doing this. I can keep taking interior products with the space of all vector fields, and I can go down, and eventually I get to degree 0, and the story ends. I get the whole de Rham complex that way. So now there is no top degree. There's no top forms in supergeometry. So I could start with, I'm going to start with the Berezinian, and I'm going to put it in degree M. And you'll notice I'm changing my notation for the Berezinian. This is a Cyrillic B for Berezin, who was Russian after all. And it turns out I could just, in a very stupid way, I could take interior product with vector fields and just keep doing it. Except now, unlike classically, it never ends. I keep going down forever. I can get down to degree 0. But then there's also degree -1 and so on. And this is actually a new complex. Oh, let me tell you how I'm defining this interior product. And like I said, it's very stupid. I'm just defining M minus P in this complex to be the Berezinian tensor the wedge of P vector fields. So these are polyvector fields on M. I take it by wedging. And I'm just defining this new complex by continuing to wedge in vector fields. And again, because everything's odd, it never ends. It never bottoms out. And so now let me state a version of Poincaré duality. It's not the version I wanted to state originally because it doesn't involve families. I haven't even gotten to the family story. And therefore, it's not due to me. So this is due to my collaborator, Simone Noha. So he proved a version where you don't take families. And the way it works is you have the de Rham complex, but now you have this new complex. And either one of them, I can choose to make them compactly supported. And there's a map that takes elements of this new complex. This is called the complex of integral forms. And if I have an ordinary form and an integral form, which I'll call omega, just to distinguish it from the previous formula, then I can wedge them together. And now wedging means pairing, right? I've said that I've defined the terms of this complex, the complex of integral forms. I've defined them to consist of the Berezinian tensor wedge products of vector fields. But wedge products of vector fields can be paired with differential forms, and that pairing gives you a function. And so what you get from this pairing of alpha with omega, that should be an omega, is you get a function times the Berezinian, times a section of the Berezinian. And that, by the things that we've said so far, can be integrated. And this induces an linear iso in cohomology, just as before. I take the cohomology in degree p of this complex of differential forms. With the cohomology in degree m minus p of this complex, this new complex, unique to supergeometry, of integral forms. And this is such a mess. And I dualize this second term. And so that's the version of Poincaré duality in supergeometry without families. Didn't get to families at all, but I've already gone way over time, so thank you very much for your attention.
Thank you very much. It was a really very nice talk. I mean, informative talk also. So, any
Thanks.
questions or comments? So maybe I will ask one of my question. So you define this super manifold, and it is quite. I mean, if we consider in the spirit of Alan Cohn's non-commutative geometry, I mean,
Yes.
is it possible to define super non-commutative manifolds and such things using C-star algebras?
I'm I don't know exactly what a super C star algebra is, but it seems very likely that it would be possible. Yeah. So I think so. But I just I don't know. I imagine someone somewhere has written about that, but I don't happen to know.
Any questions or comments? More questions or comments?
There is no restriction at all on that, similar to like in ordinary homology and cohomology to M being compact or anything like that, is there?
So in
And
the ordinary case, you don't need to assume that M is compact. You just have to take you have to take one of your complexes to be the compactly supported complex.
okay.
And you see that I've also done that here in the
Hmm.
super context. I can put this C on either factor, but I have to do it for one of them.
Is
There's
that
another, yeah, go on.
is that a big restriction? Does it make things hard?
I don't think so, but I'm not quite sure what you mean by that. What do you mean?
Uh, well, I mean, does it put a limitation on the type of results one can expect, or one needs to be particularly careful when, I don't know.
So I don't
Uh,
think so because supermanifolds, like ordinary manifolds, they have a lot of flexibility in their space of functions. They admit partitions of unity, for example, at least in this smooth context I've been considering today.
mhm.
You could also do something a little more exotic, like you could consider the space of Schwartz, the space of forms with Schwartz coefficients, like coefficients in the Schwartz space. So like instead of requiring it to vanish outside of a compact set, you just require it to decay sufficiently quickly as you go to infinity.
Mm,
The really important thing is that I be able to do the integral and get a well-defined number out of doing the integral. I don't want to have divergent integrals.
mhm. Okay, thanks.
Sure.
if there is no more questions or comments, let's thank John once more. Thank you very much, John.
Oh, thanks a
So,
lot.
2 weeks later, we will meet. We will have our next seminar. So, I hope you will all get together 2 weeks later. So, I hope we will be in contact, John. Yeah, thank you very much. Bye bye.
Yes, sounds good. Thanks for the invitation. Bye bye.
Oh.